These are the physicists who calculated, using real mathematics, that a copy of you might exist about 10 to the power of 10 to the 29th meters away. And this is how three separate branches of modern physics, that quantum mechanics, cosmic inflation, and string theory, all ended up independently pointing toward the same almost unbelievable possibility, that infinite versions of you could exist across reality. If you want more deep dives into the strangest, best documented corners of real science, get subscribed and stick around. Because this one goes further than most, all the way from a forgotten Cold War defense contractor's classified nuclear war planning to the math behind a number of possible universes so large it stopped being countable a long time ago. Let's start with the man who started it all, because the story of the multiverse is really the story of one lonely graduate student who nobody believed. His name was Hugh Everett III, and the stubbornness that would eventually define his career showed up decades before Princeton. At just 12 years old, growing up in the Washington, D.C. area, Everett wrote a letter to Albert Einstein himself, asking whether the universe was held together by something random or by something unifying. Einstein actually wrote back on June the 11th, 1943, telling the boy, in a reply that survives to this day, that there's no such thing as an irresistible force meeting an immovable body, but that there does seem to be a very stubborn boy who forced his way victoriously through strange difficulties he created for himself. It's a strange, almost prophetic detail, given what that stubborn boy would grow up to argue with the entire physics establishment about. And it's worth sitting with for a second, because a 12-year-old fooling around with a paradox letter and getting a personal, handwritten answer from the most famous scientist alive is the kind of origin story you couldn't invent if you tried. Everett's childhood wasn't entirely smooth outside of that famous letter either. His parents separated when he was young, and he was initially raised by his mother, Catherine, before moving in with his father and stepmother from around the age of 7. He won a half scholarship to St. John's College High School in Washington, a private military school, and from there moved to the nearby Catholic University of America to study chemical engineering as an undergraduate, graduating in 1953. While he was there, he came across an article on Dianetics, printed in the science fiction magazine Astounding Science Fiction, the same wave of pop psychology that would later evolve into Scientology, though Everett himself never went further with it than reading about it out of intellectual curiosity, and by most accounts, he kept a lasting preference for unconventional, natural remedies over conventional medicine for the rest of his life. From Catholic University, Everett moved to Princeton for graduate work, arriving in 1953, and it's there that the story most people actually know begins. Before getting into what Everett actually proposed, it helps to understand the specific problem he was trying to solve, because it's one of the strangest, most stubbornly unresolved puzzles in all of science, and it had already been rattling physicists for years by the time Everett showed up in Princeton. Quantum mechanics, the branch of physics that describes atoms, electrons, and light, had been worked out mostly through the 1920s by physicists including Werner Heisenberg and Erwin Schrödinger, building on ideas from Niels Bohr, who had used quantum principles as early as 1913 to explain the exact wavelengths of light given off by hydrogen atoms. What made the theory strange, right from the start, was that it didn't describe particles as having a definite location or a definite state. Instead, it described them using something called a wave function, a mathematical object that assigns probabilities to every possible outcome a measurement could produce. An electron's wave function might say there's a 50% chance of finding it here and a 50% chance of finding it over there, and until you actually measure it, quantum mechanics treats the particle as genuinely existing in both possibilities at once, a condition physicists call superposition. Bohr, working alongside colleagues in Copenhagen, built what became the standard way of explaining this, now known as the Copenhagen interpretation. Under this view, a quantum system really does exist in superposition, in a blur of possibilities, right up until the moment a measurement happens, at which point the wave function collapses and the system snaps into just one of those possible outcomes. Einstein was never comfortable with this. He's famously said to have remarked that he liked to think the moon was still there even when nobody was looking at it, capturing his broader discomfort with a physical theory that seemed to make reality depend on observation. In 1935, Einstein, working with two colleagues, Boris Podolsky and Nathan Rosen published a paper called "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?", now simply known as the EPR paper, arguing that quantum mechanics, with its apparent dependence on measurement and its strange non-local connections between distant particles, had to be an incomplete description of what's really going on. Erwin Schrödinger responded to that same paper later that same year with his own thought experiment, the one almost everyone has heard of even if they've never studied physics: a cat sealed in a box alongside a vial of poison, which will only break open if a single radioactive atom happens to decay. Since that atom exists in quantum superposition, both decayed and not decayed, the strict logic of the Copenhagen interpretation implies that the cat itself, until the box is opened, has to be treated as simultaneously alive and dead. Schrödinger wasn't proposing this as something he actually believed happened. He intended it as a kind of reductio ad absurdum, a deliberately ridiculous case meant to show how uncomfortable the Copenhagen interpretation becomes once you stop confining it to individual atoms and start applying its own logic to ordinary, everyday-sized objects. It's also, incidentally, the same paper in which Schrödinger coined the term entanglement, the word physicists still use for the strange, instantaneous correlation between particles that Einstein, Podolsky, and Rosen had pointed to in the first place. That's the puzzle Everett inherited when he arrived at Princeton in 1953, a puzzle physicists had been arguing about, without resolution, for 2 decades already. And it's genuinely a strange one, because nothing else in physics works the way wave function collapse is supposed to work. Every other equation in physics evolves smoothly and predictably over time, without any sudden, unexplained jump. Quantum mechanics never actually specifies what a measurement is, physically, or why the mere act of measuring should cause this sudden, discontinuous jump from many possibilities into one. It just asserts that it happens. Everett's solution, worked out under the supervision of the physicist John Archibald Wheeler, was to simply throw the collapse out of the theory altogether. Wheeler was one of the towering figures of 20th century physics, a man who'd go on to coin terms like black hole and wormhole, and who had himself studied directly under Bohr, making him, in a sense, physics royalty from the very school of thought Everett was about to challenge. Everett's argument, laid out across a long paper originally titled Wave Mechanics Without Probability, later renamed The Theory of the Universal Wave Function, was that the wave function never actually collapses at all. Instead, every time a measurement happens, the universe itself splits, or branches, into separate, non-interacting versions, one for each possible outcome the measurement could have produced. In this view, Schrödinger's cat isn't a paradox at all. There's a branch of reality where the cat is alive, and a branch where the cat is dead, and both are equally real. They just no longer interact with each other after the split. Everett met a woman named Nancy Gore during his 3rd year at Princeton, while he was sharing an apartment with 3 friends, and it was Nancy who ended up typing his long, technical paper by hand. Everett married her the following year. Wheeler, recognizing how radical his student's paper was, worked with Everett late into the night in his own office to revise and tighten the draft, and he ultimately decided the thesis needed a companion piece explaining it, which he wrote himself for publication alongside Everett's paper. Wheeler tried to build support for the idea before it was even published. In May of 1956, he personally traveled to Copenhagen, hoping to get a favorable reaction directly from Bohr's own circle. It didn't go the way he hoped. Then, in March and April of 1959, at Wheeler's request, Everett himself traveled to Copenhagen on what was meant to be a vacation with his wife and their baby daughter, specifically to meet with Bohr in person and try to explain his idea directly to the man whose interpretation he was challenging. By most accounts, the visit was a complete disaster. Everett simply could not get Bohr and his colleagues to take seriously the idea that the universe could be described by an objectively existing wave function that never collapses, an idea that, to them, sounded less like physics and more like heresy against everything the Copenhagen school had spent 3 decades establishing. There was a paper trail of resistance even before that trip. Not long after Everett defended his work, Wheeler received an 8-page critical review of the paper from the physicist Bryce DeWitt, who at the time was editing the proceedings of a physics conference in Chapel Hill and didn't even realize Everett's paper had originally been a doctoral thesis. Wheeler forwarded DeWitt's critique to Everett, who wrote back a 4-page response defending his reasoning. Even so, the pressure from every direction pushed Everett to trim down and soften his original thesis considerably before his committee would sign off on it, stripping out a lot of the boldest language, and Everett was never fully satisfied with the shorter, more cautious version that ultimately got published in July of 1957 in the journal Reviews of Modern Physics. He was awarded his PhD that same year, nearly a full year after he had already started his very different next job. And that's the detail most retellings skip over, because Everett didn't spend the rest of his life defending his theory inside some university physics department. In September of 1956, months before he'd even finished defending his thesis, Everett was invited to join a newly forming Pentagon organization called the Weapons Systems Evaluation Group, known as USEG, run under the Institute for Defense Analyses. Between October the 23rd and the 26th of 1956, he attended a weapons orientation course run by Sandia National Laboratories in Albuquerque, New Mexico, to learn the fundamentals of nuclear weapons, and it was there that he became genuinely enthusiastic about computer modeling as a tool for solving problems. By 1957, he was already directing USEG's Department of Physical and Mathematical Sciences, and he held that position around trips back to Princeton to finish his degree until 1964. What did Everett actually do at USEG? A large amount of it, according to the archive that later catalogued his papers, remains classified to this day. What is known is substantial enough on its own. According to Scientific American's reporting on his life, Everett's very first project for the Pentagon, the one he started before Princeton had even granted his doctorate, was calculating potential mortality rates from radioactive fallout in a nuclear conflict. He went on to work on evaluations of the Minuteman missile program as it was getting off the ground, and together with a colleague named George E. Pugh, he co-wrote a major 1959 study called The Distribution and Effects of Fallout in Large Nuclear Weapon Campaigns, published in the journal Operations Research, modeling how radioactive fallout would spread and kill in the aftermath of a large-scale nuclear war. He advised senior officials across both the Eisenhower and Kennedy administrations on how to select hydrogen bomb targets and how to structure America's nuclear triad of bombers, submarines, and missiles for maximum destructive efficiency in a first or retaliatory strike. Some accounts credit him with having written the software for the first single integrated operating plan, the actual master blueprint the United States used for how it would fight a full-scale nuclear war. And some biographical sketches also credit him with early, independent work on things like relational database software and word processing programs, decades before either concept became common in ordinary computing. None of this happened in isolation from his physics either, in an odd way, because Everett had already published serious work in game theory before any of it. Back in 1957, alongside his physics output, he had a paper included in Princeton's Annals of Mathematics Studies on what's called recursive games, work considered important enough that it was later reprinted decades afterward in a collection called Classics in Game Theory. That same mathematical toolkit, modeling decisions, outcomes, and escalating strategies mathematically, is exactly what carried over into his defense career. Princeton's own graduate school, in an obituary written after his death, credited him with helping apply game theory to the analysis of ballistic missile performance, and one biographical account describes him extending game theory into recursive structures specifically designed to model deception, escalation, and counter-strategy across multi-stage nuclear conflicts. In 1963, Everett published another piece of purely mathematical work, a paper on what's called the generalized Lagrange multiplier method for solving problems in the optimal allocation of resources, again in the journal Operations Research. It's a technical, unglamorous piece of applied mathematics, but it's a good example of the kind of thinking Everett brought to everything he touched, whether it was quantum wave functions or how to divide up a military budget, and it became the mathematical foundation for the operations research consulting work that would occupy the rest of his career. By 1964, Everett and several USEG colleagues left to found a private defense contracting firm called Lambda Corporation, and Everett became its president On July 1st, 1965, Lambda built mathematical models of anti-ballistic missile systems and designed computerized nuclear war games that, according to one of his own colleagues, were used by the American military for years afterward. Two former employees later described Lambda Corporation as responsible for a large share of the strategic analysis work that supported the systems analysis program at the Pentagon during the years Robert McNamara served as Secretary of Defense, and Princeton's obituary specifically praised Everett as a strategic advisor and analyst during the Vietnam War. Somewhere in the middle of all this Cold War contract work, Everett also got interested in Bayes' theorem, a statistical method for updating the probability of an outcome as new evidence comes in, and in 1971, he built what's been described as a prototype Bayesian machine, essentially a program designed to learn from experience and simplify decisions the way ordinary human common sense does, decades before anyone was using the term machine learning in public conversation. He also held patents connected to some of this defense and operations research work, part of the same broad thread of applying mathematical modeling to weapons performance that had defined his career since the mid-1950s. Everett stayed at Lambda until 1973, when he left to found and chair a new company called DBS Corporation, which he ran until his death, and in 1978, he even founded something called Key Travel Agency, a strange little detail that shows just how far this theoretical physicist had drifted from academic physics into the ordinary scattered life of a private defense contractor and small businessman. There's a strange kind of symmetry buried in all of this, too, one that's hard not to notice once you know the details. The same man who theorized that reality was constantly splitting into countless branching universes spent nearly 3 decades of his working life calculating exactly how many warheads it would take, and exactly where they needed to land, to destroy an enemy's ability to fight back in a nuclear war. A job that was, in its own dark way, entirely about trying to predict and control just one single, devastating branch of history. According to one obituary from Princeton's graduate school, Everett was in part responsible for applying game theory to the analysis of ballistic missile performance during a period when American nuclear strategy was being reshaped from the ground up, and none of the public reporting on his defense work suggests he ever spoke about the connection between the two halves of his career, at least not on the record. His personal life ran quietly under all of this defense work, strained in ways his own family didn't fully understand until much later. By most accounts, Everett became a heavy smoker, consuming as many as 3 packs a day, and a heavy drinker as the years went on, and he struggled with obesity, rarely if ever visiting a doctor despite it. Wheeler himself, interviewed decades later when he was 95 years old, said that Everett had seemed disappointed, perhaps even bitter, about how little reaction his theory had gotten, and Wheeler admitted he wished he had kept up their old working sessions together, because he thought the questions Everett had raised back then were genuinely important ones. Everett died of a heart attack in his home in McLean, Virginia, on the night of July the 18th into the 19th, 1982, at just 51 years old, apparently having told a colleague only days earlier that he'd lived a good life and felt satisfied with it. Here's a detail that tells you everything about how seriously Everett actually took his own theory. He was a committed, lifelong atheist, someone who, according to his biographer, had reportedly driven devout classmates at Catholic University to distraction with his relentless scientific questioning, and by his own logic, a version of him kept living on in whichever branch of the wave function he didn't die in, a concept people later started calling quantum immortality. So he told his wife Nancy that when he died, he wanted his ashes thrown out with the household trash. Nancy kept the urn for a few years before she finally went through with it. Not everyone who knew Everett dismissed his physics as a dead end either. The physicist David Deutsch, one of the founding figures of quantum computing, has said he was directly inspired by Everett's ideas after hearing lectures and having conversations about them at the University of Texas at Austin in 1977, and Deutsch has since described Everett as one of the finest minds of the 20th century. And this is where the story gets personal in a way that almost nobody expects when they first hear about quantum physics. Everett had a son, Mark Oliver Everett, who would grow up to become the lead singer of the band Eels, performing under the stage name E. Mark was 19 years old when he found his father's body in their family home, and by his own account, the two of them had barely spoken as father and son. Mark has said his father never once talked to him about his theories, that despite living under the same roof for close to 2 decades, his father felt like a stranger, like a piece of furniture sitting at the dining room table night after night, jotting down notations nobody in the house understood. Mark didn't even know his father had been a brilliant physicist until well after his death, when people outside the family started telling him who Hugh Everett III actually was. Finding his father's body that day was, in Mark's own words from his memoir, Things the Grandchildren Should Know, the only time he could remember having any physical contact with him at all. He later reflected that there was a certain value in his father's way of life, since Hugh had eaten, drunk, and smoked exactly as he pleased, and then died quickly, which Mark, having witnessed other, harder ways for people to go, came to see as not such a bad way to leave. The family tragedy didn't stop with Hugh's death either. Everett's wife Nancy died of cancer in 1998, and in 1996, Everett's daughter, Mark's older sister Elizabeth, took her own life after years of serious mental health struggles. In her suicide note, she asked that her ashes be thrown out with the garbage too, writing that she hoped it might help her end up in the correct parallel universe to meet up with her father. Mark has spoken about the toll that period took on him, and the Eels album Electroshock Blues, written during those years, is widely understood to reflect the weight of losing both his father and his sister within roughly a decade and a half of each other. There's an even darker echo to this family story. Nearly 2 decades after his father's death, on September the 11th, 2001, one of Mark's cousins was working as a flight attendant on the plane that was hijacked and flown into the Pentagon, the very building where Hugh Everett had spent so many of his working years. And Mark has said he found himself wondering whether his father's old office had been destroyed in the same attack. Years later, in 2007, Mark made a documentary about all of it, called Parallel Worlds, Parallel Lives, produced with the BBC and later aired in America on PBS as part of the Nova series, timed to roughly the 50th anniversary of his father's original 1957 thesis. In it, he travels across America meeting the scientists and colleagues who actually knew his father's work, trying to understand a man who theorized that infinite versions of reality exist, while barely existing, emotionally, for his own son. It's one of the strangest and most human footnotes in the entire history of quantum physics. A rock musician tracking down his dead father's ghost through the branching universes his father claimed were really out there. More recently, a feature documentary about Mark's own life, called The Way I Was Made, The Story of a Man Called E, has gone into production with backing from Judd Apatow and Robert Schwartzman, directed by Gus Black, promising an unflinching look at a life shaped by survival, grief, and creative persistence. So that's where the many worlds idea came from, and how it nearly got buried along with the man who invented it, and how the man behind it spent most of his working life not thinking about parallel universes at all, but about how many warheads it would take to destroy an enemy's missile silos. For roughly 2 decades after his 1957 thesis, Everett's idea sat mostly ignored inside physics. It took a physicist named Bryce DeWitt, the same DeWitt who had once written that skeptical 8-page review of Everett's original paper, working together with his graduate student Neil Graham, to properly revive the idea in the early 1970s, publishing a 1973 collection of papers under the title The Many Worlds Interpretation of Quantum Mechanics that finally gave Everett's original insight a real audience. It's DeWitt who's generally credited with popularizing the actual phrase many worlds itself, since Everett's own paper had used the more restrained term relative state formulation. But Everett never went back to physics as a career, and he died before he could see his idea earn the respect that would come afterward. One of the biggest remaining questions Everett's original paper never fully answered was a simple one. If the universe really does contain all these bizarre, branching, macroscopic superpositions, then why don't we ever actually perceive them? Why does the world we experience always look definite, with the coin already landed on one side, the cat already either alive or dead, rather than some blurry combination of both? The answer that eventually filled this gap came from a 1970 paper by the physicist Dieter Zeh at the University of Heidelberg, who showed that the ordinary equations of quantum mechanics themselves, without any need for a mysterious collapse, naturally explain why we never see these superpositions directly. The effect became known as decoherence, and it was worked out in much greater mathematical detail over the following decades by the physicist Wojciech Zurek, working at Los Alamos, along with Zare and others. The idea is that a quantum system practically never exists in total isolation. It's constantly interacting with its surrounding environment, with stray air molecules, with photons of light bouncing off it, and each of those interactions effectively leaks a tiny bit of information about the system's state out into the wider world. Zurek has pointed out, memorably, that a warm, wet, macroscopic object like a real-life cat would never stay in a coherent superposition of alive and dead for even a microsecond, because every single particle making up that cat is constantly influencing a vast number of environmental variables, making genuine quantum coherence at that scale essentially impossible to maintain. Decoherence, as Zurek and Zare worked it out, explains why we, as observers embedded inside one branch of a much larger quantum system, would only ever perceive one single, definite outcome, even if the full underlying wave function genuinely does contain every other outcome playing out in parallel, exactly as Everett had originally proposed. It's worth being upfront that decoherence, while widely accepted as physically correct, doesn't fully settle every philosophical question raised by Everett's theory on its own. Physicists and philosophers of science have pointed out that decoherence explains why we never observe strange combinations of outcomes, but it doesn't, by itself, fully explain why we experience any single definite outcome at all, rather than existing as some kind of vague blend of every branch simultaneously. That deeper question is still actively discussed today, and it's part of why the many worlds interpretation, even with decoherence bolted onto it, remains one interpretation among several, rather than a settled consensus. And there is no settled consensus, which is worth spelling out with actual numbers, because physicists have been quietly polling each other about exactly this question for decades. Back in August of 1997, Max Tegmark himself informally polled 48 participants at a conference called Fundamental Problems in Quantum Theory, held at the University of Maryland, Baltimore County, asking which interpretation of quantum mechanics they preferred. By Tegmark's own admission, the poll was highly informal, but the results were striking anyway. The Copenhagen interpretation still got the most votes, but many worlds came in a close second, ahead of other named alternatives, and Tegmark said at the time that it indicated a striking shift in opinion compared to the era when Copenhagen simply reigned supreme without challenge. In 2013, physicists Maximilian Schlosshauer, Johannes Koffler, and Anton Zeilinger ran a more carefully constructed poll of 33 participants at a conference in Austria organized by Zeilinger himself, and found that Copenhagen still led with 42% of respondents naming it their favorite interpretation, while many worlds came in at 18%, well ahead of alternatives like Bohmian mechanics, which nobody in that particular poll picked as their favorite at all. That same survey found that 64% of respondents agreed that randomness is a fundamental feature of nature, with about half of those saying that randomness is genuinely irreducible, and when asked directly whether they thought Bohr's original view of quantum mechanics was simply wrong, 27% of respondents said yes. 30% said Bohr was correct or would eventually be shown to be correct, and another 30% said the question needed more time before anyone could really say either way, a genuinely three-way split on the very physicist whose interpretation Everett had once been shut down for challenging. The most recent and by far the largest of these surveys came from the journal Nature itself, published in 2025 to mark the 100th anniversary of quantum mechanics, polling more than 1,100 researchers. Once again, Copenhagen came out on top, but with only 36% support, meaning less than 2 out of every 5 physicists actually favor what's traditionally been called the mainstream interpretation. Many worlds came in at 15%, a figure that's remarkably close to where it stood over a decade earlier in the Schlosshauer, Koffler, and Zeilinger poll, suggesting the many worlds camp inside physics has settled into a genuine, stable minority position rather than either fading away or taking over. Bohmian mechanics, a completely different interpretation built around hidden variables and what's called a pilot wave, picked up 7%. Perhaps the most telling number in the entire 2025 survey came from a physicist named Renato Renner, who studies quantum foundations at ETH Zurich, and who was struck by how few of the respondents were actually confident in their own answer. Only 24% of physicists in that survey said they believed their own favorite interpretation was actually factually correct. In other words, a century after quantum mechanics was developed, and nearly 70 years after Everett proposed his branching alternative to Bohr's collapsing wave function, the overwhelming majority of working physicists still aren't sure which picture of reality is the right one, even as they use the same mathematics every single day to build lasers, computer chips, and everything else quantum mechanics makes possible. By the time we reach the 2000s, this branching universe concept was no longer standing alone in the world of speculative physics. A physicist named Max Tegmark, working at what was then the University of Pennsylvania, published a paper in 2003 called simply Parallel Universes, and followed it up with a more detailed 2009 survey paper called The Multiverse Hierarchy. In both, he did something clever. He didn't just defend Everett's quantum branching, he organized every serious multiverse theory in physics into a hierarchy, sorted by how strange and how speculative each one gets. And he called these 4 levels of the multiverse. Level 1 is by far the least controversial, and it comes straight out of standard cosmology rather than anything exotic. If space is infinite, which current observations genuinely allow for, then the universe doesn't run out of room to repeat itself. Tegmark's argument is built on a simple idea that in an infinite universe, every physically possible arrangement of matter has to occur again somewhere, and in fact it has to occur an infinite number of times. Using calculations based on the physical limits of how many particle states can exist in a region of space at a given temperature, essentially asking how many protons could be packed into a Hubble volume no hotter than 100 million Kelvin, Tegmark estimated that the nearest exact duplicate of U specifically would sit somewhere around 10 to the power of 10 to the 28th or 29th meters away, depending on which version of his calculation you're reading, since he's published slightly different figures across different papers. That number is so large it's functionally meaningless to picture, but the reasoning behind it is straightforward math applied to an extremely vast, possibly infinite universe. Tegmark separately calculated that a sphere of radius 100 light-years, identical to the 100 light-year sphere centered on us, meaning every human perception and event within it would match ours exactly for the next century, should exist somewhere around 10 to the power of 10 to the 92nd meters away. And the nearest region of space, identical to our entire observable universe, an exact duplicate Hubble volume down to the last detail, should sit even farther out, at distances he's put anywhere from 10 to the power of 10 to the 115th, to 10 to the power of 10 to the 118th meters, again, depending on the specific paper and the specific assumptions used. These aren't places we could ever reach, because the observable universe itself is roughly 93 billion light-years across, and anything beyond our cosmic horizon is, by definition, forever outside what light has had time to reach us from since the beginning. Level 2 takes things a step further, and it leans on a completely different area of physics, called cosmic inflation, and this is where one of the great, almost accidental discoveries in the history of science comes into the story. On the night of December 6, 1979, a 32-year-old postdoctoral researcher named Alan Guth was working late at the Stanford Linear Accelerator Center on an obscure problem involving particles called magnetic monopoles, a problem that had nothing to do with cosmology, when he realized that the same mechanism he'd been using to solve that problem could also explain 2 much bigger cosmological puzzles at once: why the universe appears so close to perfectly flat, and why conditions look so uniform across regions of space that, under ordinary Big Bang physics, should never have had time to influence each other at all. Guth was so excited by the realization that he wrote, in all capital letters, across the top of a fresh page in his notebook, the words, "Spectacular Realization," and drew a double box around it. He got on his bike the next morning and rode to his office in a personal speed record. One of the first people he told was the physicist Leonard Susskind, who reportedly responded by joking that the most amazing thing about it all was that physicists actually got paid to do this kind of work. Guth's theory, which he called inflation, proposed that in an incredibly brief fraction of a second after the Big Bang, our universe underwent an exponential burst of expansion, doubling in size dozens of times over and ballooning from something smaller than a subatomic particle into a volume vastly larger than anything we can currently observe. It's worth noting that Guth wasn't entirely alone in reaching this kind of idea. A Soviet physicist named Alexei Starobinsky had developed his own, more mathematically complicated inflationary model earlier in 1979, though it remained relatively unknown outside the Soviet Union at the time, and it was Guth's simpler, more accessible version that ended up reshaping the field. A physicist named Andrei Linde, who later moved to Stanford University, built on all of this through the 1970s and 80s, first showing in work from 1974 through 1978 that the energy of a scalar field could act the way vacuum energy does in Einstein's equations, laying groundwork for Guth's model, and then, in 1982, proposing his own new inflationary universe scenario that fixed technical problems in Guth's original version. Linde went further still, with a version called eternal inflation, worked out through the 1980s, in which inflation doesn't actually stop everywhere at once. Instead, it keeps happening forever in most places, spinning off countless separate bubble universes that each stop inflating on their own independent schedule, becoming what we'd call individual Big Bangs. Level 2 says that these other bubble universes could have completely different physical constants than ours, different particle behavior, potentially even different numbers of spatial dimensions, because whatever physics gets locked in during the end of each bubble's inflation might be randomly different from bubble to bubble. Observationally, inflation itself has held up reasonably well. Later satellite missions studying the leftover heat from the Big Bang, the cosmic microwave background, including NASA's WMAP satellite, found that the universe really is close to flat, and really is remarkably uniform across huge distances, exactly the kind of evidence inflation was originally invoked to explain. And those same missions found that the universe is made up of roughly 74% dark energy, 22% dark matter, and only about 4% of the ordinary visible matter that makes up stars, planets, and everything we can directly see. Level 3 is where Everett comes back into the picture, because this is Tegmark's label for the many worlds interpretation itself. The idea that unitary quantum mechanics, meaning quantum mechanics without any collapse, naturally produces branching universes every time a measurement happens, with decoherence, the mechanism worked out by Zare and Zurich, explaining why we only ever perceive one branch from the inside. What's interesting is that Tegmark points out something almost ironic here. He argues that Level 3 technically doesn't add any genuinely new type of universe that Levels 1 and 2 haven't already accounted for in some form, and yet Level 3, the quantum branching idea, has historically been the single most controversial of the four, precisely because it was the one that directly attacked the established Copenhagen interpretation that most physicists had been trained on for decades. Level 4 is the strangest of the bunch, and even people who study this stuff for a living tend to treat it as the most speculative. This is Tegmark's idea that other universes could be built on entirely different mathematical structures, not just different physical constants, but different fundamental equations altogether. It's tied to what Tegmark calls the mathematical universe hypothesis, the notion that mathematical existence and physical existence are ultimately the same thing, so that any mathematically consistent structure might, in some sense, physically exist. It's the level furthest from anything resembling an experiment, and it edges more into philosophy than testable physics. Before going further into the string theory side of this story, it's worth explaining where the reasoning that ties all these levels together actually comes from, because it has its own specific origin point too. The idea that we should expect to find ourselves in a universe compatible with our own existence, rather than being surprised when we do, is called the anthropic principle, and the term itself was coined by the astrophysicist Brandon Carter at a 1973 symposium in Krakow, Poland, held to celebrate the 500th anniversary of the birth of Copernicus. Carter's point was almost a direct response to Copernicus. Copernicus had shown that Earth isn't the center of the universe, kicking off centuries of scientific thinking built around the idea that humanity doesn't occupy any special or privileged position in the cosmos. Carter argued that this reasoning had been pushed too far, because our very position as observers necessarily has to be privileged in at least one sense. We can only ever find ourselves existing in a place, and at a time, compatible with the fact that we exist to do the observing at all. Carter distinguished between a weak version of this idea, essentially just a reminder to account for that observer bias when interpreting cosmological data, and a stronger version, suggesting the fundamental parameters of the universe must permit the creation of observers at some stage. The idea got a much bigger public platform in 1986, with a book called The Anthropic Cosmological Principle by physicists John Barrow and Frank Tipler, which became the most widely cited reference on the topic, even though it framed the argument somewhat differently than Carter originally had, and even though a lot of working cosmologists reportedly found it more than a little exasperating at the time. Now, Level 2 and Level 4 both eventually connect to one of the strangest chapters in modern theoretical physics, something called the string theory landscape, and it deserves its own deep dive, because the math behind it produces numbers that make even Tegmark's distances look small by comparison. String theory, for physicists who work on it, is an attempt to describe all the particles and forces of nature as tiny vibrating strings rather than point particles. And one mathematical requirement of the theory is that it needs extra spatial dimensions beyond the three we experience day to day. Dimensions that get curled up or compactified into shapes far too small to detect directly, often described using complex geometric objects called Calabi-Yau manifolds. The trouble is, there are an enormous number of different ways to curl up those extra dimensions, and each different way produces a different possible universe, with different values for the constants of nature. In the year 2000, physicists Raphael Bousso and Joseph Polchinski published a paper on what's called flux compactification, showing that when you thread these extra hidden dimensions with generalized versions of magnetic flux, essentially a mathematical generalization of the same kind of flux that describes ordinary magnetic fields, you don't get one single answer for how the universe should look. You get an exponentially large number of possible stable configurations, and they pointed out that this could offer a way to explain, anthropically, why the cosmological constant of our own universe is so puzzlingly small. 3 years later, in 2003, a paper by physicists Shamit Kachru, Renata Kalosh, Andre Linder, and Sandip Trivedi, now commonly just called after their initials, built on that work and constructed an actual mechanism for stabilizing all of these extra hidden dimensions into fixed values, producing stable four-dimensional universes with the kind of small positive cosmological constant we actually observe. Leonard Susskind himself has described the cult construction, admiringly, as a kind of Rube Goldberg mechanism, meaning a solution that works, but through an elaborate, jury-rigged combination of separate pieces rather than one clean, elegant answer. Less than a month after that KLT paper came out, Susskind published his own paper called The Anthropic Landscape of String Theory, which is generally treated as the founding document of what one prominent critic later dubbed Multiverse mania inside theoretical physics. Susskind argued that string theory doesn't just allow for a large number of possible stable universes, it allows for a landscape of them, and that reasoning anthropically about which of those universes could support observers like us was a legitimate way to explain otherwise mysterious features of the physical constants we measure. He later expanded these ideas into a popular book in 2005 called The Cosmic Landscape, String Theory, and the Illusion of Intelligent Design. So how many universes are we actually talking about here? The commonly quoted figure, first estimated by physicist Michael Douglas using the flux compactification framework, and refined further in follow-up papers by Douglas working with Ashok and separately with Denef, put the number of possible stable string theory vacua at somewhere around 10 to the power of 500. To put that in perspective, that's a 1 followed by 500 zeros, a number so much larger than the total number of atoms in the observable universe that ordinary comparisons stop meaning anything, and that figure hasn't stood still since 2003. Later analyses of a specific corner of the landscape called F-theory compactifications by physicists Washington Taylor and Yinan Wang pushed the estimate as high as 10 to the power of 10 to the fifth, an unimaginably larger number still, and other technical papers in the years since have floated figures as extreme as 10 to the power of 272,000 for certain classes of flux vacua. Interestingly, physicists Lance Dixon and Jeffrey Harvey have pointed out that an even bigger number, 10 to the power of 1500, actually showed up in their own 1986 paper on constructing four-dimensional string theories, years before the anthropic landscape became a popular topic, though they've noted that number gets quoted out of context just as often as the more famous 10 to the power of 500 figure does, since it wasn't originally meant as an estimate of physically viable universes at all, just a demonstration that four-dimensional string theory wasn't unique. This landscape is exactly what feeds into Tegmark's Level 2 and Level 4 multiverses. Because if there really are that many mathematically consistent ways for a universe to be built, and if something like eternal inflation is constantly creating new bubble universes that could settle into any one of those configurations, then you end up with a multiverse on a scale that dwarfs even the distances involved in Level 1. And it's precisely this landscape that reignited the argument over whether reasoning about universes we can never observe still counts as doing physics at all. And that brings us to the argument that never really gets settled, the testability debate, because a huge number of serious physicists think this entire framework, at least beyond Level 1, runs into a fundamental problem that has nothing to do with the math and everything to do with what counts as science in the first place. The philosopher of science Karl Popper argued, decades ago, that for an idea to count as scientific, it has to be falsifiable, meaning there has to be some observation or experiment that could, in principle, prove it wrong. Physicist Sabine Hossenfelder has been one of the most vocal modern critics applying that standard to the multiverse, arguing repeatedly that ideas like the Level 2 and Level 4 multiverses are untestable by definition, since any other universe, by the very way it's described, is something we could never observe or interact with, meaning there's no experiment that could ever confirm or rule it out. She's put it plainly, in the sense that the multiverse might be interesting to think about and fun to discuss, but that doesn't make it science, because a hypothesis needs to be falsifiable to earn that label. She's gone further still in some of her writing, arguing that mistaking mathematics for physical reality is the central problem with the whole framework, and that simply saying every possible value of a constant exists somewhere doesn't actually explain anything, since a theory with no assumptions at all, strictly speaking, isn't really a theory. She's not alone in this. Physicists including Paul Steinhardt, George Ellis, Joe Silk, and Paul Davies have all raised versions of the same objection over the years, that a theory which can never be tested against reality is fundamentally different from something like general relativity, which makes specific, checkable predictions that could, in principle, have failed. Theoretical physicist Peter Voigt, writing on his blog Not Even Wrong, has tracked what he calls 15 years of multiverse mania inside the field, arguing that the entire anthropic landscape program amounts to an argument against string theory ever producing testable predictions at all, rather than a genuine scientific breakthrough, and disagreements over exactly this question have at times turned into fairly public, occasionally personal disputes between physicists on opposing sides of the debate. On the other side of that argument, you've got physicists like Brian Greene, Leonard Susskind, Sean Carroll, and Tegmark himself, who argue that testability doesn't have to apply to every single consequence of a theory, only to the overall framework producing it. Their logic goes like this. If a well-tested model, like inflationary cosmology, predicts a multiverse as a natural side effect of math we already trust, then it's reasonable to take that side effect seriously, even if we can never directly observe the other universes it implies. And here's the strongest piece of ammunition the pro-multiverse side actually has. A case where anthropic reasoning arguably made a real, checkable prediction before the data came in. Back in 1987, physicist Steven Weinberg, a Nobel laureate, used anthropic reasoning to tackle one of the biggest embarrassments in theoretical physics: the fact that ordinary quantum field theory predicts the vacuum energy of empty space, the cosmological constant, should be around 120 orders of magnitude larger than anything we could possibly observe, a value so large it would have caused the universe to fly apart or collapse before galaxies or stars or anyone capable of asking the question could ever have formed. Weinberg reasoned that if the cosmological constant really can take on a range of different values across some larger landscape of possibilities, then the fact we exist to measure it at all tells us it can't be much bigger than the tiny value needed to still allow galaxies to form. He predicted, specifically, that the cosmological constant should turn out to be small, but not exactly zero. In 1998, more than a decade later, astronomers studying distant supernovae discovered that the expansion of the universe really is accelerating, evidence for exactly the kind of small, non-zero vacuum energy Weinberg's anthropic argument had pointed toward years earlier. A lot of physicists consider this one of the only genuine predictive successes anthropic reasoning about a multiverse has ever produced, and it's the example defenders of the framework tend to reach for first whenever the testability question comes up. Critics counter that Weinberg's argument required assuming a specific landscape of possible values in the first place, an assumption that itself can't be independently tested, so even this success story doesn't fully settle the argument either way, and some technical follow-up work has pointed out that Weinberg's original calculation actually favored a somewhat larger cosmological constant than the one we've actually measured, meaning the prediction, while directionally correct, wasn't a perfect match either. There's an even stranger problem that's emerged from taking eternal inflation seriously, one that even physicists sympathetic to the multiverse treat as a genuine, unresolved headache, called the measure problem, and it leads to something called the Boltzmann brain problem. If inflation really is eternal, producing an infinite number of bubble universes forever, then any calculation of how likely a particular observer is to see the universe we actually see runs into trouble, because you're always dividing one infinity by another, and different mathematical ways of handling that division, called different measures, produce wildly different, sometimes contradictory predictions. One especially strange consequence, explored by physicists including Andreas Albrecht, Lorenzo Sorbo, Raphael Bousso, and others, is that if the universe truly settles into a stable, low-energy vacuum state for an effectively unlimited stretch of time, then over unimaginably long timescales, random quantum fluctuations in otherwise empty space could occasionally assemble a fully formed, self-aware brain, complete with false memories of an entire life that never actually happened, a so-called Boltzmann brain. Because it's statistically far easier for a stray quantum fluctuation to randomly assemble one isolated brain than it is to produce an entire orderly galaxy full of planets and evolved observers, some measures of the eternally inflating multiverse actually predict that these random, freak Boltzmann brains should vastly outnumber ordinary observers like us across the full multiverse. An outcome physicists, including Alan Guth himself, have worked to try to rule out through more careful choices of how you measure probability across an infinite structure. If a particular version of the multiverse predicts that the typical observer should be a Boltzmann brain rather than someone like you, sitting somewhere reading or listening to a normal ordered account of history, then that version of the theory is treated as having failed some basic sanity check, which is exactly why physicists like Guth, Vilenkin, and others have spent so much effort trying to construct measures of the infinite multiverse that avoid this problem altogether. That disagreement, roughly, is where things still stand. There's no consensus inside physics on whether ideas beyond level 1 deserve to be called scientific theories in the strict Popperian sense, or whether they're better described as mathematically motivated speculation that happens to be enormously fun to think about. It's an active, sometimes heated argument between some of the most respected physicists alive, not a settled dispute with a clear winner, and it comes up again every time a new paper on the string landscape or a new observation of the cosmic microwave background gets published. There's one more piece of the puzzle worth digging into here, because it connects Everett's original idea directly to some of the most advanced technology being built today, and it comes from someone who actually met Everett in person. The physicist David Deutsch, widely regarded as one of the founders of quantum computing, first encountered Everett's ideas directly through lectures and conversations at the University of Texas at Austin in 1977, in a meeting that was reportedly arranged by Bryce DeWitt himself. By Deutsch's own account, Everett came across as intense, a heavy chain smoker, genuinely enthusiastic about the idea of parallel universes, in contrast to the far more cautious relative states language Wheeler had originally pushed him to use in his published thesis. Deutsch went on to propose the concept of a universal quantum computer in 1985, and in his 1997 book, The Fabric of Reality, he laid out an argument that quantum computers only really make intuitive sense if you accept something like Everett's many worlds interpretation. His reasoning is that a quantum computer solves certain problems by effectively performing an enormous number of separate calculations simultaneously, calculations that would need vastly more physical resources, more particles, and more raw computational substance than exist in our single observable universe to carry out all at once, which led Deutsch to argue that a working quantum computer is, in a very real sense, borrowing computational power from parallel versions of itself, running in other branches of the multiverse. Deutsch has pointed out that even something as ordinary as the classic double-slit experiment, in which single particles fired one at a time somehow build up an interference pattern as though each one were interfering with itself, only makes complete sense in his view if you accept that there are other, shadow versions of that particle traveling through the other slit in a parallel branch, exerting a real, measurable influence on the branch we observe. Deutsch's arguments haven't settled the interpretation debate either, and other physicists have pushed back on exactly how tightly quantum computing is really tied to many worlds specifically, since the same equations that describe a working quantum computer are equally compatible with several other interpretations of quantum mechanics. But the broader phenomenon Deutsch is pointing to, entanglement, and the strange correlations between separated particles that so unsettled Einstein back in 1935, has since been confirmed about as thoroughly as any result in physics ever has been. In 2022, the Nobel Prize in Physics was awarded jointly to Alain Aspect, John Clauser, and Anton Zeilinger, specifically for experiments demonstrating the violation of what's called Bell's inequality, a mathematical limit worked out by the physicist John Stuart Bell in the 1960s, on how correlated two separated particles could possibly be if the universe worked the way Einstein hoped, through simple, local hidden variables, rather than genuine quantum weirdness. Clauser ran the earliest versions of these tests in the 1970s. Aspect closed major loopholes in the experiment during the 1980s, and Zeilinger's group went on to push the technology further still, demonstrating things like quantum teleportation of a particle's state across a distance. Every single one of these tests has come out the same way, confirming that quantum mechanics really does produce the strange, non-local correlations Einstein found so uncomfortable, which doesn't by itself prove Everett's many worlds interpretation correct over its rivals, but it does confirm, beyond any reasonable scientific doubt, that the underlying weirdness Everett was trying to make sense of back in 1957 is a genuine, experimentally verified feature of how reality actually behaves. Given how seriously Everett personally believed in the consequences of his own theory, it's worth returning to the darkest and strangest thread this whole story produces, something physics eventually formalized as a thought experiment called quantum suicide. The idea was first published independently by the roboticist Hans Moravec in 1987 and the mathematician Bruno Marchal in 1988, and it was developed further and popularized by Max Tegmark himself in 1997 and 1998. The setup takes Schrödinger's cat and flips the perspective around, putting the observer inside the box instead of the cat. Picture a device that measures the quantum spin of a fresh particle every few seconds, and depending on the outcome, either fires a fatal shot or produces nothing more than an audible click. Under the ordinary, Copenhagen-style view of quantum mechanics, a person running this experiment repeatedly would eventually, almost certainly, be killed, since the odds of surviving any given number of trials shrink rapidly toward zero. But under Everett's many worlds interpretation, the argument goes differently. Every time the trigger is pulled, the universe branches, and in every single branch where the person is still alive to notice anything at all, they only ever experience surviving, because there's no branch in which a dead person perceives being dead. Followed to its logical extreme, this reasoning implies that from the subjective, first-person perspective of the experimenter, they would always find themselves continuing to survive an arbitrarily long sequence of these trials, a conclusion some physicists and philosophers, including Tegmark, have described as pointing toward a kind of quantum immortality, at least when viewed strictly from the inside of one's own uninterrupted experience. It's worth being clear that this remains a contested thought experiment rather than an established prediction. Most physicists who take Everett's theory seriously still argue that it says nothing about what an outside observer, watching the experimenter from a normal external vantage point, would see, since from any perspective other than the experimenter's own, the vast majority of branches simply end in ordinary death. Given that Hugh Everett himself apparently structured the disposal of his own remains around a belief that some version of him would carry on in whichever branch he survived in, it's hard not to read the entire quantum suicide debate as physics quietly working out, decades later, exactly the kind of personal conviction Everett seems to have held about his own theory all along. It's worth stepping back for a moment to note just how far this once obscure, nearly abandoned physics thesis has traveled into popular culture, because the distance is genuinely enormous. In March of 2023, the film Everything Everywhere All at Once, an absurdist story about a laundromat owner who learns to connect with parallel versions of herself across the multiverse, swept the Academy Awards, winning 7 Oscars, including Best Picture, making it, by some measures, the most awarded film of all time. Its writer-directors, Daniel Kwan and Daniel Scheinert, have said they drew heavily on real physics while developing the script, and Kwan has specifically credited a non-fiction book called Worlds Without End: The Many Lives of the Multiverse, by the religious studies scholar Mary Jane Rubenstein, as one of the guiding lights behind the film's treatment of infinity and its philosophical stakes. Tegmark himself, when asked about the film by the Washington Post, joked that he genuinely tries to console himself over minor bad luck, like getting a parking ticket, by imagining there's a parallel branch of reality where he didn't get ticketed at all, and presumably another branch where his car got towed instead. Physicist Brian Greene, in his own book, The Hidden Reality, has gone as far as cataloguing 9 mathematically distinct categories of multiverse that show up across different corners of theoretical physics, of which Everett's many worlds branching is just one. Everything Everywhere All at Once is really just the most decorated entry in what's become an entire wave of multiverse storytelling. Marvel's cinematic universe has leaned on the concept repeatedly, through Spider-Man: No Way Home, which brought together 3 separate actors who had each previously played Peter Parker in their own distinct film continuities, through Doctor Strange in the Multiverse of Madness, through the animated Spider-Man: Into the Spider-Verse and its sequel, and through television series like Loki and What If. The animated series Rick and Morty has built years of episodes around the idea of infinite branching timelines, treating the concept almost as a running structural gag as much as a plot device. None of these stories are rigorous physics, and the version of multiverse most of them use is a much looser, more flexible idea than anything Everett, Tegmark, or the string theorists actually argue for in their papers. But the underlying inspiration, traced all the way back, keeps coming back to the same place. A lonely graduate student's rejected 1957 thesis, and the phrase Bryce DeWitt eventually gave it: many worlds. It's worth pausing on Wheeler himself for a moment, because the mentor behind Everett's radical thesis was, in his own right, one of the strangest and most important physicists of the 20th century, and understanding him helps explain why Everett's idea survived at all, instead of simply vanishing. Wheeler earned his doctorate at Johns Hopkins University in 1933, at just 21 years old, and traveled to Denmark shortly afterward, specifically to study under Niels Bohr, writing in his own fellowship application that he wanted to work with Bohr because, in Wheeler's words, Bohr sees further than any man alive. In 1939, Wheeler and Bohr co-published the first paper to explain nuclear fission using quantum theory, and Wheeler went on to work on the Manhattan Project during the Second World War, later contributing to the development of the hydrogen bomb as well. After the war, Wheeler became one of the physicists most responsible for reviving serious interest in Einstein's general relativity inside the United States, at a time when the subject had drifted to the margins of physics. He coined or popularized an entire vocabulary that's now completely standard in physics and even everyday language, including black hole, which he began using in public lectures in 1967 to describe the endpoint of a collapsing star, wormhole, which he introduced in 1957 to describe hypothetical tunnels through space-time, quantum foam, and the phrase "it from bit," capturing his later career interest in the idea that information itself might be more fundamental to physical reality than matter or energy. Stephen Hawking once called Wheeler the hero of the black hole story. He was also known, by his own students and colleagues, for a teaching style built around riddles, wordplay, and deliberately open-ended questions rather than direct answers, a style some younger physicists reportedly found opaque even as most of them respected him deeply. Wheeler mentored an extraordinary number of future leading physicists over a teaching career that spanned nearly 4 decades at Princeton, before he moved to the University of Texas at Austin from 1976 to 1986, the very university where a young David Deutsch would later encounter Everett's ideas directly. It's genuinely remarkable, in hindsight, that a physicist this influential, this close to Bohr personally, and this central to the mainstream development of physics, was the one willing to supervise, defend, and eventually publish a companion piece supporting Everett's direct challenge to Bohr's own interpretation of quantum mechanics. Wheeler never fully abandoned his allegiance to Bohr's broader framework during his lifetime, but he clearly took Everett's underlying questions seriously enough to keep defending the seriousness of the work decades later, telling an interviewer, when he was 95 years old, that he wished he'd kept up their working sessions together, and that the questions Everett had raised were genuinely important ones physics still needed to reckon with. It's worth spending a little more time on the actual people behind that K-T paper too, because the story of how it came together has its own human texture. Andrei Linder met the physicist Renata Kalosh while they were both students at the Lebedev Physical Institute in Moscow in the mid-1970s, and the two married in 1977, going on to become genuine scientific collaborators as well as spouses. Both eventually left the Soviet Union, Kalosh moving through CERN before joining Stanford University's physics faculty in 1990, and Linder following her there the same year, where the two of them have continued to publish on inflationary cosmology together ever since. According to Stanford's own account of how the K-T paper actually came about, the whole thing started early in 2003 with an email from the physicist Shamit Kachru, who was visiting his eventual co-author Sandip Trivedi in India at the time, containing an idea that had apparently occurred to Kachru during a layover in New Delhi. Kalosh plotted the data Kachru sent her and found a dip in potential energy on her computer screen that matched a prediction her Stanford colleague Eva Silverstein had made separately, generated through completely different string theory assumptions, and it was seeing that match appear on her own screen that convinced her the four of them were onto something real. Kachru later described the appeal of the collaboration partly in terms of how differently each of the four authors approached the problem, noting that Kalosh came from a background in supergravity, Linde from inflationary cosmology, and Trivedi and Kachru himself from more purely mathematical string theory, which is part of why the resulting construction ended up getting so much more attention from the wider physics community than earlier, narrower attempts at the same problem. It was precisely this cult construction that Michael Douglas and his collaborator Frederick Denef, both at Rutgers University at the time, used to calculate their now famous estimate of roughly 10 to the power of 500 distinct possible universes. It's worth understanding a bit more about Leonard Susskind himself too, since he keeps showing up at almost every turn of this story, from Guth's original 1979 celebration through the founding of the anthropic landscape argument in 2003. Susskind, born in New York City in 1940, is one of at least 3 physicists who independently realized around 1970 that a mathematical model then being used to describe the strong nuclear force could actually be reinterpreted as describing tiny vibrating strings, work that helped kick off string theory as a field in the first place. Decades later, in 1995, building on ideas from the Dutch physicist Gerard Hooft, Susskind gave the first precise string theory version of something called the holographic principle, the idea that all the physical information contained inside a given region of space can, in principle, be fully encoded on that region's boundary, the same way a 2-dimensional hologram can encode a full 3-dimensional image. Susskind became known to the wider public for what he called the Black Hole War, a long-running, high-profile disagreement with Stephen Hawking over whether information that falls into a black hole is truly destroyed forever, or merely scrambled and eventually released as the black hole evaporates. Susskind argued for years that basic quantum mechanics forbids information from being genuinely destroyed, and in 2004, Hawking formally conceded a related bet he'd made with the physicist John Preskill, a concession widely read within physics as vindicating Susskind's side of that particular argument, a story Susskind later told at length in his book The Black Hole War. Given his central role in kicking off the anthropic landscape argument in 2003, it's fitting that Susskind also ended up in one of the more public confrontations over exactly the testability question this whole video keeps circling back to. In March of 2006, Susskind took part in a recorded public debate with the physicist Lee Smolin, specifically over the anthropic principle and the string theory landscape, each arguing opposite sides of essentially the same dispute that Hossenfelder, Steinhardt, and others would keep having with Green, Carroll, and Tegmark for years afterward. It's a debate that, in one form or another, still hasn't produced a winner, and probably never will, since it isn't really a disagreement about mathematics at all. It's a disagreement about what counts as doing physics once your calculations start describing things no experiment could ever reach. The most up-to-date snapshot of exactly how unsettled all of this remains came out only a couple of months before this video, in May of 2026, when the physicist Nyayesh Afshordi and 3 co-authors published results from something called the Big Mysteries Survey, run through the American Physical Society's own physics magazine, gathering responses from 1,675 physicists and physics-adjacent respondents on exactly the kind of foundational questions this whole story keeps circling back to. The survey asked directly about the fine-tuning problem, the puzzle of why the fundamental constants of nature seem to sit in the narrow range required for stars, chemistry, and life to exist at all, framing it as a choice between 3 broad explanations: a multiverse in which every possible value gets realized somewhere, an intelligent designer, or the constants simply being brute, unexplained facts about reality that don't require any further justification. None of the 3 options won a majority. The single most popular answer, chosen by 26% of respondents, was that the constants are brute facts, needing no further explanation, and even when the multiverse and intelligent design answers were added together, they still only accounted for 28.8% of responses combined, falling short of a majority either way. The same survey found similarly split opinions on other supposedly settled questions in cosmology. On dark energy specifically, the plain cosmological constant explanation, the simplest textbook answer, only picked up 24% support, actually trailing a competing explanation involving a time-varying dark energy field, which got 25.9%, meaning the textbook answer to what's driving the universe's accelerating expansion isn't even the leading opinion among physicists who responded. And on the Big Bang itself, 68% of respondents, in both this large survey and a smaller companion survey of physicists in Copenhagen, agreed that the Big Bang should really be understood only as a description of the universe evolving from an early hot, dense state, rather than as proof that time itself had a definite beginning, a distinction that runs directly against how the Big Bang tends to get described in casual popular science coverage. Taken all together, the picture that emerges, a full century after quantum mechanics was developed, and nearly 70 years after Everett proposed his branching alternative to wave function collapse, is a field where almost none of the biggest questions about the ultimate structure of reality have anything close to a settled, majority consensus, and where the multiverse, in one form or another, keeps showing up as a live, seriously debated possibility, rather than either a fringe idea or an accepted fact. There's a strange twist buried in the word multiverse itself too, one that has nothing to do with physics at all in its origin. The earliest known use of the actual word multiverse comes from the American philosopher and psychologist William James, who wrote, in 1895, that visible nature is all plasticity and indifference, a multiverse, as one might call it, and not a universe, using the term to describe his sense that the visible world lacked any single unifying moral order, not to describe parallel physical realities at all. It took decades for the word to drift toward the meaning it has today. Before Everett ever proposed his branching quantum universes, the Argentinian writer Jorge Luis Borges published a short story in 1941 called The Garden of Forking Paths, describing a labyrinth of branching, converging, and diverging timelines in which, in his own words, in most of those times, we do not exist. In some, you exist, but I do not. In others, I do, and you do not. In others still, we both do. A description that reads almost like a plain language summary of Everett's physics, written 16 years before Everett wrote the actual physics down. Even stranger, in 1952, 5 years before Everett's thesis, the physicist Erwin Schrödinger himself gave a lecture in Dublin in which he raised, apparently at least partly in jest, the possibility that the different mathematical outcomes described by his own equations might not be alternatives at all, but might all genuinely happen simultaneously, a strikingly early hint of exactly the idea Everett would later develop into a full, rigorous physical theory. None of this makes Everett's contribution any less original, since he was the one who actually worked out the mathematics and built a coherent physical framework out of the idea. But it's a good reminder that the intuition behind branching realities had been floating around philosophy and literature for decades before physics caught up to it. That same underlying tension over whether string theory and its landscape of possible universes even deserves to be treated as science boiled over publicly in 2006 in what a number of physicists and science writers started calling the String Wars. That year saw the publication of 2 separate popular books attacking string theory head-on: The Trouble with Physics, The Rise of String Theory, The Fall of a Science, and What Comes Next, by the physicist Lee Smolin, a co-founder of the Perimeter Institute for Theoretical Physics, and not even wrong. The Failure of String Theory and the Search for Unity in Physical Law, by the Columbia University mathematician and physicist Peter Voigt, whose blog of the same name is the same one that later tracked what he called 15 years of multiverse mania. Both books argued, in different tones and with different degrees of technical detail, that string theory had consumed several decades and enormous amounts of academic talent and funding without producing a single testable, falsifiable prediction, with Voigt going so far as to compare the situation to the physicist Sheldon Glashow's own earlier comparison of string theory to medieval theology, a body of elaborate, internally consistent reasoning that nonetheless couldn't be checked against experiment. String theorists and their defenders pushed back hard at the time, arguing that theoretical physics has always required long periods of mathematical development before experimental tests become possible, and that dismissing an entire research program because it hasn't yet produced a clean prediction ignores how difficult it is to test physics at the energy scales string theory actually operates at. Neither side fully won that argument either, and it's the same basic disagreement, dressed up in slightly different language, that keeps resurfacing every time Hossenfelder, Steinhardt, or Voigt square off against Susskind, Green, or Carroll over whether the multiverse belongs in physics textbooks or in the philosophy section of the library. This exact argument, whether a working quantum computer counts as evidence of other universes doing part of the computation, actually made global headlines as recently as December of 2024, which shows just how alive this debate still is. Google unveiled a new quantum computing chip called Willow on December 9, 2024, built with 105 qubits, and announced that it had completed a benchmark calculation in under 5 minutes that would take one of today's fastest ordinary supercomputers an estimated 10 septillion years, a number so large it vastly exceeds the age of the universe itself. In the company's own blog post announcing the chip, Google's quantum AI lead, Hartmut Neven, wrote that this performance lends credence to the notion that quantum computation occurs in many parallel universes, in line with the idea that we live in a multiverse, explicitly crediting the idea to David Deutsch. It was reportedly the first time a major tech company had tied its own product announcement directly to the many worlds interpretation of quantum mechanics, and the claim immediately drew pushback from physicists. Sabine Hossenfelder pointed out on social media that the specific benchmark Willow completed, called random circuit sampling, produces a random distribution with no practical real-world use on its own, and she also noted that Google's earlier, similar quantum supremacy claim from 2019 had already been challenged by IBM, which later argued that an ordinary classical computer could perform an equivalent version of that same task in a few days, rather than the thousands of years originally claimed. Other physicists were quick to point out that conventional quantum mechanics already explains why quantum computers can be so fast, without necessarily requiring the existence of literal parallel universes doing part of the work, meaning Willow's genuinely impressive engineering achievement doesn't actually settle the interpretation debate one way or the other. But the fact that a Google executive felt comfortable invoking Everett's theory by name in a mainstream corporate announcement covered by outlets from Newsweek to the Associated Press, says something about how far this once obscure, nearly buried 1957 thesis has traveled, from a rejected Princeton dissertation to a defense contractor's classified nuclear war games, to a line in a Silicon Valley press release about the fastest computer chip in the world. There's one more piece of Wheeler's own physics worth mentioning here, because it captures, in a single thought experiment, exactly the same strangeness about observation and reality that pushed Everett toward his branching universes in the first place. In 1978, Wheeler proposed what's now called the delayed choice experiment, a variation on the classic double-slit setup in which the experimenter's decision about how to measure a photon, whether to look for wave-like or particle-like behavior, is delayed until after the photon has already passed through the slits. Under the strict logic of the standard interpretation, this means a choice made in the present moment appears to determine, retroactively, whether the photon behaved like a wave or a particle earlier in its journey, at least according to the way physicists often describe the outcome. Wheeler himself framed this as an argument against the idea that quantum particles have fixed, definite properties independent of how and when they're eventually measured, rather than as evidence of literal time travel or backward causation, and physicists still debate the exact philosophical implications of the result today, with some more recent theoretical work specifically arguing that the delayed choice experiments don't actually require anything as dramatic as effects preceding their causes. Versions of Wheeler's experiment have since been carried out in real laboratories, using single photons, atomic memory systems, and increasingly sophisticated quantum eraser setups, and they've consistently produced the same strange result the thought experiment predicted. It's exactly the kind of unresolved weirdness about what a measurement even physically is. The same unresolved weirdness Everett was staring at back in 1953. And it's a good reminder that 70 years of experimental progress in quantum mechanics has done an enormous amount to confirm the theory's predictions with extraordinary precision, without coming anywhere close to settling what any of it actually means about the underlying nature of reality. It's worth going a little deeper into the decoherence story too, because physicists have kept refining it since Zer's original 1970 paper, and one of the more recent developments has its own memorable name, Wojciech Zurek, the same physicist who helped work out the mathematical details of decoherence at Los Alamos, later extended the idea into something he calls quantum Darwinism. The basic insight is that the environment surrounding any quantum system doesn't just randomly destroy delicate superpositions, it actively selects a small number of preferred stable states, the ones Zurek calls pointer states, and then copies information about those specific states redundantly across huge numbers of the surrounding particles, photons, and other environmental degrees of freedom. Zurek's term borrows the language of biological natural selection quite deliberately, since the idea is that certain quantum states are, in effect, more fit to survive contact with a noisy environment than others, and it's specifically those fit, redundantly copied states that end up being the ones multiple independent observers can agree on when they each separately measure a system and compare notes. This gives decoherence theory an answer, of sorts, to why the classical, everyday world we experience looks so stable and objective, and why different observers, watching the same experiment from different angles, reliably see the same outcome rather than each perceiving their own private version of events. It doesn't, on its own, decide the argument between many worlds and its rival interpretations, since decoherence, combined with quantum Darwinism, is broadly compatible with several different pictures of what's really happening underneath. But it does mean that even physicists who reject Everett's specific branching universe language have had to take seriously the deeper mechanical question he was the first to push hard on. Why does a quantum system that's supposedly a blur of possibilities ever end up looking, from any observer's perspective, like one single, definite thing? The disagreement over anthropic reasoning hasn't stayed confined to physics conferences either, since the multiverse keeps getting pulled into a much older argument about design and purpose in the universe. In July of 2021, the cosmologist Luke Barnes took part in a public discussion, released as part of a series called The Big Conversation, arguing that the fine-tuning of physical constants points toward a designer, framing the multiverse as, in his view, no better an explanation than invoking God directly. since both, in his telling, are ultimately untestable appeals to something outside the observable universe, to explain why the constants of nature look the way they do. Sabine Hossenfelder has pushed back on that framing directly, arguing that the two explanations aren't actually equivalent, and that at least some multiverse theories are grounded in mathematical frameworks, like inflationary cosmology, that make other testable predictions elsewhere, even if the specific claim about other universes can't itself be checked. It's a genuinely strange alliance of critics on this particular question, since Hossenfelder herself is deeply skeptical of the multiverse on ordinary scientific grounds, and yet she still resists the argument, favored by some religious commentators, that her own skepticism somehow supports the case for a designer instead. The debate has never fully resolved, and it probably can't, since it ultimately hinges on a philosophical question, whether an explanation has to be testable to be considered legitimate at all, that sits upstream of any specific physics, whether that's Everett's branching quantum worlds, Guth and Linde's eternally inflating bubbles, or Cachru, Kalosh, Linde, and Trivedi's landscape of string theory vacua. There's a more technical wrinkle buried inside Everett's own theory that's worth mentioning too, one that even sympathetic physicists and philosophers still argue about, called the preferred basis problem. The issue is this: the mathematics of quantum mechanics doesn't, by itself, specify a single, unique way to split a combined quantum system into separate, well-defined worlds. You can describe the same underlying wave function using many different, mathically equivalent bases, or coordinate systems, and depending on which one you pick, the branching structure of the multiverse can look completely different. Decoherence, as worked out by Zare and Zurich, goes a long way towards solving this in practice, since interactions with the environment naturally pick out specific, stable pointer states as the ones that actually persist and get copied redundantly, effectively selecting the basis that matches our everyday, classical experience of a world made of definite objects in definite places. But philosophers of physics have pointed out that this solution is approximate and depends on details of how a given physical system interacts with its surroundings, rather than following as a strict, exact mathematical necessity from the equations alone, which is part of why the many worlds interpretation, even 7 decades after Everett proposed it, still has technical loose ends that working physicists continue to publish papers trying to tie down. There's a more recent and genuinely unresolved wrinkle in this whole story that's worth bringing in too, because it strikes directly at the mathematical foundation the entire anthropic landscape argument depends on. Starting in 2005, the physicist Qumrun Vafa and a growing network of collaborators began developing what's called the Swampland program, an effort to map out which seemingly consistent low-energy theories are actually compatible with a full theory of quantum gravity, and which ones only look consistent while secretly hiding a contradiction, a category Vafa named the Swampland as the opposite of the landscape. In 2018, Vafa and several co-authors, including the physicist Paul Steinhardt, one of the same physicists who has spent years arguing against the testability of the multiverse on more general grounds, published papers arguing that string theory might not actually be able to produce stable universes with a small positive cosmological constant at all, the exact kind of universe the 2003 KKTLT construction was built specifically to produce, and the exact kind of universe we appear to actually live in. If Vafa's Swampland conjecture holds up, it would mean the Kelt mechanism and the entire 10 to the power of 500 landscape calculation built on top of it might rest on constructions that only look valid, but that secretly fail once quantum gravity is treated fully rigorously. The physicists who built the original Kelt construction have pushed back hard. Eva Silverstein, a Stanford physicist who separately developed her own approach to constructing similar universes, and who happens to be married to Shamit Kachru, one of Kult's own co-authors, joked to a science journalist that her family finds itself besieged by these conjectures, and argued that the Swampland papers rely on limited and, in her view, questionable analyses rather than a decisive proof. Other physicists in the field, including the string theorist and cosmologist Matthew Kleban, have described the Swampland conjecture as highly speculative, since the overwhelming majority of the string landscape remains completely unexplored, making any sweeping claim about what can or can't exist within it hard to fully trust either way. Whether Vafa turns out to be right, and whether that would genuinely falsify large parts of string theory the way some of his supporters hope, or whether the cult side of the argument holds up under further scrutiny, remains a live, actively contested question inside theoretical physics today, which is itself a pretty striking fact on its own. More than 2 decades after the 10 to the power of 500 number first grabbed the public imagination, physicists still don't agree on whether the universes in that landscape are even mathematically real to begin with. It's worth mentioning how we actually came to know so much of Everett's personal story in the first place, since so much of his career was classified or simply undocumented for decades. Most of the detailed biographical material used throughout this account, the WSEG timeline, the Lambda Corporation years, the family details, comes from the investigative reporter Peter Burns' 2010 biography, The Many Worlds of Hugh Everett III, Multiple Universes, Mutual Assured Destruction, and the Meltdown of a Nuclear Family, published by Oxford University Press. Byrne had an advantage most potential biographers of Everett never would have had: the direct cooperation of Mark Oliver Everett, whose own musical career and 2007 documentary had already reopened the family's history in a way that made a fuller, more honest biography possible. Reviewers have noted that the book carefully avoids turning into simple hero worship, since Byrne doesn't shy away from Everett's very real personal shortcomings: the drinking, the emotional distance from his family, the strange combination of genuine intellectual brilliance and difficulty functioning as a father or husband, alongside the historical record of a physicist whose most important idea barely survived his own lifetime. It's a thoughtful account, by most reviewers' assessment, of a genuinely original figure caught at the intersection of some of the most consequential science and the most consequential defense policy of the entire Cold War, sitting right alongside the story of one family quietly falling apart underneath all of it. It's also worth noting that the intuition behind branching, multiplying realities goes back even further than Borges or William James, all the way to ancient Greek philosophy. The philosopher Democritus, working around the 5th century BCE, believed the universe was built out of tiny, indivisible atoms moving through an infinite void, atoms that, given enough time and enough space to work with, would eventually combine and recombine in every conceivable arrangement, meaning the specific world we happen to observe around us would be just one arrangement among a genuinely unlimited number of others, all equally certain to appear somewhere in that same infinite void. It's a strikingly similar intuition to Tegmark's Level 1 multiverse, worked out nearly 2,500 years before Tegmark had the mathematics of modern cosmology available to actually calculate the distances involved. Guth and Lind, and the Russian physicist Alexei Starobinsky, whose independent, more complicated version of inflation had come slightly earlier in 1979, were jointly awarded the Kavli Prize in Astrophysics in 2014, recognizing all 3 of them together for their contributions to inflationary cosmology, decades after Guth's original notebook page with spectacular realization written across the top in all capital letters. Guth had gone, within a matter of months after his original insight, from a physicist so uncertain about his own job prospects that he described himself as looking smart without having accomplished anything important, to someone fielding job offers from 10 different universities, eventually settling permanently at MIT, where he still works today, and where his original notebook itself now sits on public display at the Adler Planetarium in Chicago, a strange little museum artifact documenting the exact night modern cosmology's leading theory of the universe's first fraction of a second was born. So where does all of this actually leave us, after everything this story has covered? Level 1, the idea that space is big enough to repeat itself somewhere out beyond our cosmic horizon, is treated by most working cosmologists as a fairly ordinary consequence of an infinite or extremely large universe. Not something exotic, just something extremely far away, built on nothing more speculative than counting how many possible arrangements of matter a given volume of space could contain. Level 2 rides on the back of cosmic inflation, a theory with genuinely strong indirect observational support from missions like WMAP and Planck, even though the eternal, endlessly bubble-spawning version of it, and the string landscape that might fill those bubbles with different physical constants, remains unconfirmed, and, as the ongoing swampland dispute shows, still contested, even at the level of pure mathematics. Level 3, Everett's many worlds interpretation, has gone from being nearly laughed out of physics in the 1950s, dismissed by Bohr's own circle in Copenhagen, softened and trimmed down before Everett's own committee would even approve it, to being one of the most seriously discussed interpretations of quantum mechanics by the 1990s and onward, sitting right alongside the Copenhagen interpretation as a live option rather than a fringe one, even though the field, according to the most recent surveys taken in 2025, still hasn't settled on it, with barely more than a third of physicists even agreeing on Copenhagen itself, and fewer than a quarter of physicists confident their own preferred interpretation is actually correct. And level 4 remains the outlier, treated by many physicists as closer to a mathematical philosophy than a physical prediction anyone genuinely expects to confirm. What ties this whole story together, from a 12-year-old writing a mischievous letter to Einstein and getting a handwritten reply calling him a stubborn boy, to a Princeton graduate student getting shut down by Niels Bohr's generation of physicists in a Copenhagen meeting that went nowhere, to that same man spending the next 2 decades calculating nuclear fallout patterns and missile targeting strategies for the Pentagon, instead of defending the theory that would eventually make him famous, all while quietly building a career in game theory, operations research, and eventually early machine learning that ran almost entirely in parallel to the physics no one wanted to hear about, to a son who barely knew his own father finding him dead at 19, and only later discovering, from strangers, that his dad had theorized about infinite branching realities, to a daughter who took her own life believing she'd find her father again in the correct branch of the multiverse, to physicists today calculating distances so vast they can't be pictured, arguing over whether 10 to the power of 500 possible universes counts as physics or as philosophy, watching a tech company invoke a 70-year-old rejected thesis to explain why its newest computer chip is fast, is a single, almost absurd possibility, that the reality you're experiencing right now, reading or listening to this exact sentence, might not be the only one, that somewhere, whether 10 to the 29th meters away, in an endless stretch of ordinary space, containing a version of you finishing this sentence in an identical room, or in another quantum branch that peeled away from this exact moment, the instant some unnoticed atom somewhere decided to decay or not decay, or in some bubble universe running on entirely different physical constants, built from a landscape of mathematical possibilities so large that physicists still argue about whether the number even means anything, there could be another version of you. Some physicists, people like Max Tegmark, Brian Greene, Leonard Susskind, and Sean Carroll, take that seriously, not as a leap of faith, but as a mathematical consequence of theories, quantum mechanics and cosmic inflation, that have already been tested and confirmed in every other respect we know how to check. Others, physicists like Sabine Hossenfelder, Paul Steinhardt, George Ellis, and Peter Voigt, think it's an idea that will never be more than an elegant, untestable story, no matter how much good mathematics gets built underneath it, because a theory that can never be checked against reality, in their view, has quietly stopped being physics at all. Neither side has won that argument, and there's a reasonable chance neither side ever will, because it isn't really a dispute that more data can settle. It's a dispute about what we're willing to call knowledge in the first place, when the thing we're trying to know about is, by its very definition, forever beyond our reach. Hugh Everett believed his own answer to that question deeply enough that he arranged for his own remains to be thrown out with the household trash, trusting that some version of him would carry on regardless. His son found him one afternoon in 1982, a stranger in his own house, and spent the rest of his life, on stage under a different name, in a memoir, in a documentary made 25 years later, slowly working out exactly who that stranger had actually been. Somewhere between those two facts, a rejected Princeton thesis and a rock musician's grief, sits 70 years of physics that still hasn't decided whether it's describing the deepest structure of everything that exists, or just the most beautiful mistake modern science has ever made. It's worth circling back to Max Tegmark himself for a moment, since his own 4-level hierarchy is the backbone connecting so much of this story together, and he's got his own personal brush with the exact idea he'd go on to build a career studying. In 2014, Tegmark published his own popular science book, Our Mathematical Universe, My Quest for the Ultimate Nature of Reality, through Knopf. And the book opens with an anecdote about riding his bike to school one morning in 1985 and narrowly avoiding being killed by a passing truck, before immediately noting that in some other branch of reality, by his own theory's logic, a version of Max Tegmark wasn't so lucky and never grew up to become the cosmologist writing that very book. The book went on to become a bestseller, reviewed favorably by outlets including the New York Times, which described it as combining an informative survey of genuine recent developments in astrophysics and quantum theory with Tegmark's own, more controversial argument that physical reality and mathematics are ultimately the same thing. Tegmark holds a PhD from the University of California, Berkeley, is a physics professor at MIT, and also serves as president of an organization called the Future of Life Institute, and he's been quoted noting that multiple universes went, within the space of just a couple of decades, from being treated as a fringe, almost crackpot idea on the margins of physics, to something a meaningful share of working cosmologists now consider a serious, live possibility. A shift he's been given a good deal of credit for helping drive through his own persistent, methodical case for taking the whole framework seriously. There's one more genuinely thorny technical problem worth explaining, because it's the single objection that comes up most often from physicists who are otherwise sympathetic to Everett's basic branching universe picture. Standard quantum mechanics doesn't just say outcomes are possible, it assigns each outcome a specific numerical probability, using something called the Born rule. And those probabilities have been tested to extraordinary precision in laboratories for decades. But if Everett's theory is right, and every possible outcome of a quantum measurement genuinely happens in some branch or another, then what does it even mean to say one outcome is more probable than another? If a measurement has two possible results, and the universe branches into both of them regardless of the underlying odds, there's a real philosophical puzzle in explaining why we should expect to find ourselves, in our own particular branch, seeing the specific statistical pattern the Born rule predicts, rather than treating both branches as equally likely just because both of them equally exist somewhere in the wave function. Physicists sympathetic to many worlds have proposed several different ways to try to recover the Born rule from Everett's framework, rather than simply assuming it, including approaches based on counting branches weighted by something called the amplitude of the wave function, and David Deutsch's own attempt, mentioned earlier, to derive the rule using a form of decision theory that doesn't presuppose probability as a starting ingredient at all, reasoning instead about how a perfectly rational agent inside the theory ought to bet on future outcomes. None of these approaches has become a fully settled, universally accepted solution, and it remains one of the more active technical battlegrounds among physicists and philosophers who take the many worlds interpretation seriously enough to spend their careers trying to patch its remaining gaps, which is really just one more example of the broader pattern running through this entire story. The closer you look at any single piece of the multiverse, from Everett's original branching quantum worlds, to Guth and Linde's endlessly inflating bubbles, to Katru, Kalosh, Linde, and Trivedi's landscape of string theory vacua, the more you find serious, unresolved argument sitting right underneath the elegant headline version of the idea. It's worth putting a real number on how flat the universe actually appears to be, since that flatness is one of the two original puzzles Guth's inflation was built to explain in the first place. The Planck satellite's final full mission results, released in 2018, combined with independent measurements of the large-scale distribution of galaxies, constrained the universe's spatial curvature to a value of essentially zero, with an uncertainty of only about 2 parts in 1,000, a level of flatness that would be an almost impossible coincidence without something like inflation to smooth it out in the universe's first fraction of a second. It's worth being honest that this measurement hasn't ended all argument either. Some later reanalyses of the same Planck data have found hints of a very slight preference for a universe with a small amount of positive curvature rather than being perfectly flat, a minor, ongoing disagreement inside cosmology, sometimes called the curvature tension, though the majority of cosmologists studying the question still consider the case for an extremely flat, or perfectly flat, universe to be on solid observational ground once every available dataset gets combined together. Not every legendary physicist connected to this story took Everett's side either, and it's worth being clear about that. Richard Feynman, who had studied under the same John Wheeler who supervised Everett's thesis, was openly dismissive of the many worlds interpretation later in his career, writing in a 1982 paper that he saw no coherent way to make sense of splitting both worlds and the observers inside them, and suggesting that people who favor the interpretation mostly just keep repeating the same technical defenses: the preferred basis problem, the recovery of correct probabilities, questions about identity across branches, until the strangeness of the whole idea stops registering as strange. It's a pointed dismissal from one of the most respected physicists of the 20th century, though other physicists who've studied Feynman's fuller body of writing on the subject, including the decoherence pioneer Dieter Zeh, have noted that Feynman also separately acknowledged the same basic conceptual difficulty Everett was responding to in the first place: that a truly universal wave function logically seems to force you toward accepting the equal reality of an enormous number of possible worlds, even while Feynman himself stopped short of drawing that conclusion all the way through. The scale of the disagreement over what to make of all this is really nothing new. Erwin Schrödinger himself, giving a lecture in Dublin in 1952, 5 years before Everett's thesis, described the ordinary quantum theorist as talking constantly about probabilities and alternatives, while noting that the far stranger possibility that those supposed alternatives might not be alternatives at all, but might simply all happen at once, tends to strike most physicists as close to lunacy, something they'd dismiss as leading to a kind of formless, blurred quagmire version of reality if it were actually true. Schrödinger clearly meant that as a criticism of taking his own equations too literally. 5 years later, Everett built an entire physical theory out of taking them exactly that literally, and nearly 70 years after that, according to the most recent large-scale surveys, something close to 1 in 6 working physicists agree with him. It helps to put an actual number on how fast decoherence really happens, because the speed involved is part of why nobody has ever managed to observe a macroscopic superposition directly. According to a February 2026 feature in Quanta magazine, covering Zurich's continuing work on the subject, a simple dust grain floating in ordinary air, struck by stray photons and surrounding gas molecules, will decohere in roughly 10 to the negative 31st seconds, a duration so short it comes out to about 1/1,000,000th of the time it takes a single beam of light to cross the width of one proton. Decoherence, in other words, isn't some slow, gradual fading of quantum weirdness. It's closer to instantaneous the moment any macroscopic object makes even the faintest contact with its surrounding environment, which is exactly why nobody walking around in the ordinary, everyday world ever bumps into a genuinely blurred, half-real version of a coffee cup or a set of car keys. Even if Everett's full theory says a version of that blurriness translated into full branching universes rather than a fading interference pattern might still be happening underneath everything, every single moment, all the way down. It's worth noting, before wrapping up, that not every alternative to Everett's picture shares the same testability problem that dogs the higher levels of Tegmark's hierarchy, because there's a genuinely testable rival still being actively investigated in labs today. A family of theories called objective collapse models, including one developed by the physicists Giancarlo Girardi, Alberto Rimini, and Tullio Weber, generally known by their initials as GRW, propose modifying the actual mathematics of quantum mechanics itself, adding a small, spontaneous, random localization process that becomes overwhelmingly likely to trigger as more and more particles get combined into a single system. Unlike both the Copenhagen interpretation and Everett's many worlds picture, which are built to reproduce the exact same experimental predictions as ordinary quantum mechanics, and are therefore experimentally indistinguishable from each other in practice, collapse models like GRW actually predict small, specific departures from standard quantum behavior for sufficiently large objects, deviations that current experiments, including delicate optomechanical setups using microscopic mechanical mirrors and cantilevers, are actively searching for. So far, none of those experiments have found any departure from ordinary quantum mechanics, and each new null result narrows the range of parameters collapse models are still allowed to use without contradicting the data. It's a useful point of contrast for the whole story this video has been telling. because it shows that physicists absolutely do know how to build genuinely falsifiable alternatives to standard quantum theory when they want to, which makes the persistent, decades-long argument over whether the many worlds interpretation and its cosmological cousins count as real science even sharper. It isn't that testability is impossible in principle, it's that Everett's specific branching universe picture, along with eternal inflation's bubbles and the string theory landscape, all happen to sit on the untestable side of that particular line, at least with the experimental tools physicists have available today. Zeilinger's own contributions kept building well past his 2022 Nobel Prize too, and they show just how far entanglement research has traveled from a purely philosophical puzzle into genuine, deployed infrastructure. In 1997, Zeilinger achieved the first experimental demonstration of quantum teleportation, transferring the quantum state of one particle onto another without physically moving the original particle between them. One of his own doctoral students, the physicist Jianwei Pan, went on to lead a Chinese research team that used a satellite named Mikius, launched in August of 2016 as part of a $100 million joint Chinese-Austrian program to distribute entangled photon pairs to ground stations in China, separated by more than 1,200 kilometers, smashing the previous entanglement distance record of roughly 100 kilometers set using ordinary fiber optic cables. In 2017, Zeilinger himself took part in a secure quantum call between Vienna and Beijing, using keys generated through the Mikius satellite to encrypt a conversation across more than 7,600 kilometers, calling it a first step toward a genuinely global, tap-proof quantum internet. None of this settles the argument over Everett's specific interpretation of what's happening underneath entanglement, but it's a vivid reminder that the same strange, non-local correlations Einstein dismissed as spooky action at a distance back in 1935, the exact phenomenon Everett was trying to make coherent sense of in his own thesis 22 years later, has since become the working foundation of a real, functioning, space-based communications technology. And that, in the end, is the arc this whole story traces. A quantum mystery nobody could explain in 1935 became a rejected physics thesis in 1957, became 2 decades of silence, while its author built nuclear war plans for the Pentagon instead, became a slowly rehabilitated, seriously debated interpretation by the 1990s, became 4 escalating levels of cosmological speculation by the 2000s, became a landscape of 10 to the power of 500 mathematically possible universes still argued over today, and became, somewhere along the way, satellites relaying secret messages through entangled photons, a tech company crediting its fastest chip to parallel universes, and a family of grieving musicians and physicists all quietly wondering whether some other version of the people they lost might still be out there, in a branch of reality none of us will ever be able to visit, but that the mathematics, so far, refuses to rule out. There's one more detail from those physicist surveys worth including, because it captures the mood of the field better than almost anything else in this story. When Christoph Sommer ran his own version of the interpretation poll in 2013, modeled directly on the earlier Schlosshauer, Koffler and Zeilinger survey, he added an option to the list of possible favorite interpretations that hadn't been offered before, simply called "shut up and calculate," a phrase long used half-jokingly to describe physicists who use quantum mechanics constantly and successfully in their work, while declining to take any position at all on what it actually means about the underlying nature of reality. That option performed well. It's a fitting place to end, honestly, since it captures something true about this entire 70-year argument. The mathematics of quantum mechanics has never once failed a single experimental test physicists have thrown at it, from Bell inequality violations to satellites relaying entangled photons across continents, and every one of the 4 levels in Tegmark's hierarchy, however speculative, is built directly on top of that same unbroken mathematical foundation. What nobody agrees on, not Everett's committee in 1957, not Bohr's circle in Copenhagen, not the 1,100 physicists surveyed by Nature in 2025, is what any of it actually means, or how many of you there might really be out there to hear it. It's worth going back to Everett's own mother for a moment too, since the pattern of mental illness that would eventually touch his daughter Elizabeth reached back at least one more generation before Hugh Everett was even born. His mother, Catherine, known to family as KK, spent time in a mental hospital, by some accounts more than once, during Everett's own childhood. She was also, in her own right, a published writer, placing stories and poems in literary magazines over the course of her life, with subjects that reportedly included metaphysics and space, decades before her son would grow up to make his own scientific mark on exactly those same themes. A posthumous collection of her poetry was eventually published in her old university's alumni magazine, authorized by Hugh Everett III himself. It's a small, easily overlooked detail buried inside a much larger story, but it adds one more layer to an already strange family history. A grandmother writing about space and the nature of reality in her poetry. A father building an entire physical theory about the branching structure of reality itself. A daughter convinced she'd find him again in exactly the right branch of it. And a son who spent decades of his own life, on stage and on the page, trying to make sense of all three of them at once. Wheeler himself, late in his career, pushed his own thinking on observation and reality even further than the delayed choice experiment, developing something he called the participatory anthropic principle, the idea that observers aren't just passive witnesses to a universe that already exists independently of them, but are, in some deep sense, active participants whose observations help bring the specific, definite history of the universe into being in the first place. It's a genuinely radical idea, even by the standards of everything else in this story, treating the entire history of the cosmos as something not fully settled until it's been observed, and Wheeler, characteristically, never fully spelled out exactly how literally he meant it, preferring to let the phrase itself provoke the kind of open-ended questioning he built his entire teaching career around. It's not hard to see, looking back, why a physicist willing to entertain an idea that's strange would also be the one willing to supervise, defend, and quietly champion his own students' far stranger proposal that the universe never really settles into one single history at all. If you've made it this far, you've now got a fuller picture of where the idea of infinite parallel U's actually comes from than most people who casually reference the multiverse in conversation ever bother to dig into. The real, verifiable history behind a phrase that gets thrown around constantly in movies, comic books, and casual conversation, usually stripped of almost everything that makes it genuinely interesting. It didn't start with a screenwriter. It started with a 12-year-old's letter to Einstein, a rejected Princeton thesis, a defense contractor calculating nuclear fallout, and a family that spent decades quietly living out the emotional weight of an idea most of them barely understood, while its author was still alive to explain it. Thanks for sticking around for the whole story, and if you want more deep dives like this one, into the strangest, most rigorously sourced corners of real science and the equally strange people behind it, you know what to do. One last number to leave you with. The observable universe, the portion of all of existence that light has actually had time to reach us from since the beginning, is about 93 billion light-years across, and everything in it, every galaxy, every star, every planet, every person who has ever lived, sits inside that single, finite sphere. Tegmark's own calculations suggest that an identical copy of that entire sphere, matter for matter, atom for atom, sits somewhere around 10 to the power of 10 to the 115th meters beyond it, in a stretch of space so vast that the distance between here and there dwarfs the size of the observable universe itself by a margin that no ordinary number can meaningfully express. Whether that copy, or the branching quantum worlds inside Everett's wave function, or the bubble universes inside Guth and Lindy's eternally inflating cosmos, or the landscape of 10 to the power of 500 string theory vacua, actually exist in any sense a physicist would be willing to call real, is still, 70 years after a stubborn Princeton graduate student first sat down to work out the mathematics, very much an open question.